Hello, everybody. Wow, that's loud. Thanks for having me here. Ted asked me to tell you about the backend of Mapillary and how we do things, and so here I am coming back. This is actually a continuation of a talk I did for I think 3 or 4 years ago on Docker that we use in Mapillary. So let's see how much has happened. So for you who don't know what we do at Mapillary, just a very short intro. What is Mapillary? Mapillary is a Malmö-based company. We crowdsource 2D imagery. Whoa, this is a bit small, right? Maybe we should, like this. We crowdsource imagery, 2D imagery, and we extract from that as the source of ground truth. We extract map objects and help fix the world's map with actual information that comes from automatic extraction. We started late 2013. There's around 90,000 contributors that submit about 1 million images each, a day. There's now 400 million images, doubling every half year. So it's quite a lot of data. From that, we extract right now 50 billion map objects. So it's a lot of data that needs to be handled. This data is then available via APIs to OpenStreetMap, disaster recovery, municipalities, departments of transportation, anybody that needs ground truth to be good and processed and up to date. Also, we are opening a lot of our key components for research, for open source, like our viewers, fully open source, our apps are getting open sourced, and a lot of things. We try to contribute as much as we can. So what does it look like? How does this work? So basically, there's the capture part. People submit imagery in any form from any dash cam or GoPro or via the apps. The only thing we need is geolocation and maybe offset to the track that they're recording, so we have the image direction, so we can have an idea of where things are and how they overlap. They upload this to Mapillary via scripts and apps and whatnot. After that, we process things. We do basically 3 things. One is semantic segmentation, which means we're looking at a 2D image, and right now in isolation, going forward even like within the context of the other imagery in a sequence or spatially. And we try to classify every pixel in that image into different classes, like building or street marking or fire hydrant or whatnot, like bicyclists and so on. We also classify especially volatile objects, which are interesting for the next step, which is a 3D reconstruction, which means we are 3D interpolating overlapping images into a sparse point cloud, you can call it. And in the third step, we, again, in that process, we take away what we perceive as volatile objects and polygons, for instance, sky, playing children and other moving objects that are not good for matching on. We are trying to stay at the static side of things so we can match things. And then in the last step, we apply the rest of the semantic segmentation again to these voxels. So we have segmented point clouds that we then apply clustering algorithms and other interesting stuff in 3D to extract map objects, right? So we will see if I can get this up via my phone. I should be able to. Let's see, where's my, oh, it's there. Let's see if we get, oh. Here we got something. So this is a little video just like shortly explaining the process that I just said we do. So you see like 360 images taken in Amsterdam by the city of Amsterdam that imported like 2 million of these in Amsterdam. There's other imagery, but this corner is only 3D, right? And they match with each other. You see that in the viewer. This is the 3D reconstruction of that corner just from these images, nothing else, right? And you can zoom out, you get basically a reconstructed view of the city. And then if you apply the semantic segmentation, you will see that we color the pixels by class, basically. So the red ones are cars, the green ones are trees, and the blue ones are buildings and lane markings and so on. And from that, then, you can start to, let's see what we're doing here. We're clustering small, groups of street lamp voxels into point objects that are then street lamps, and that's what you can get via the API. So citywide, it looks something like that. So this is a relative point cloud. It gets anchored at the GPS points, so we don't know exactly how big it is, but through the GPS, we know like where to anchor it, right? So there's of course all sorts of other objects. So this is basically what comes out and what people are interested in. For OpenStreetMap, this is awesome because they can suddenly see all the fire hydrants in Paris and check if they are correct and so on. And of course, map providers and automotive wants to have updated high definition maps and so on. So there's a lot of uses for this, right? So this was just like an introduction on what we do. Deployment-wise, like how are we developing? So basically, we started with Mapillary Docker-based deployment when Mesos just got Docker support in 2014. And at that point, it was very stable. Nowadays, you have Kubernetes and other Docker fabrics that you can deploy to. We still use Mesos. It works reasonably well. For long-running jobs, we use Marathon on top of Mesos, since Mesos is just a scheduling framework, while Marathon is actually translating Docker containers and their constraints into resource demands that Mesos can understand, right? Also, in that direction, we tag actually things that need to be deployed on different levels. So all our services basically are Docker containers. And I will get back to why this is like interesting to us. And we then have both stateful and stateless scaling. Most of the stateless scaling we just do by putting jobs onto RabbitMQ, and then deploying a number of Docker containers who acts as workers on that. And when they're done and have, for instance, scaled images or other stateless jobs, they post their results to, say, S3 or others, and they act that message. If not, for instance, because of auto-scaling, jobs get interrupted, the message doesn't get acted, and the next worker will come in and work on that. That's kind of stateless scaling. For the stateful scaling, we use a framework called Apache Storm, which basically reads off what we have as our event sourcing queue, Kafka. We could have done more complicated stuff, but Kafka seems to work reasonably well, and we don't need a lot of filtering and so on. So we just like raw read these topics and filter on the client if we don't need all events that come through there, right? And then Storm reads messages in batches. I can show you what a Kafka topic would look like. I could actually just so this is our fire hose. So let's go to Mapillary All, where there's a lot of messages. So this is what would come out here. Let's see when it actually connects. You see, this is not the full thing, but you see a number of JSON events that we then send through these queues, and we serialize, deserialize them on the producer consumer. So this is basically the main event bus for stateful processing in Mapillary. And then you see sequence dirtied and locker unlocked and whatnot. There's like lots of stuff going on. And then Storm is, we have an extension on top of Storm, a stream processing framework, which is called Trident. And with Trident, we can guarantee order, and we can guarantee exactly one semantics, which means things are coming in exactly the same order as they come in Kafka, which keeps strict order. and we can guarantee that if you break down in the middle of a batch, say the database is corrupt or whatever, like the machine's going down, then we can continue at exactly the tuple that we were at when we left that batch. So that's pretty interesting too. Another interesting fact is that we can, within a batch, aggregate things in caches and then just submit the sum of cache changes as transactions to the databases. We recently had a case where the number of database transactions was actually exceeding what Postgres can handle because we used an old Rails backend, which does like microtransactions basically. Anything you do is reflected in the database, and yeah, we almost ran out of the 2 billion transaction IDs that you can have in Postgres, which was interesting. At that point, Postgres locks until it has vacuumed everything, which in our case was 5 weeks. You don't want that. So we're very grateful for this. So this is basically what we do, and then we have different Docker containers for different things, right? So we use different Docker containers for image processing, for running these Storm supervisors and whatnot, and then we do auto scaling on Amazon based on basically two tiers. If you look at this, our monitoring stack is based on Riemann. It's a little stream server that is basically like a React server. Let me see if it updates anytime soon. That is a lot of graphs, so that's why this is a bit slow. Here we go. So we have two types of scalings. We have different marathon scalers. Here you see the number of containers of different types that we scale depending on how many measures we have in the queues and the load on the actual applications. So the one up there is SFM atomic, that's structure for motion atomic. So that's a merging process that merges these images together, which is right now scaling. Everything's scaling down because the number of images is going down. So we do dynamic scaling, right? And here it's slowly going up, so the scaling is building up. So this will deploy more of the same on Marathon and Mesos. Then we are monitoring Mesos, and we have on the different Docker containers constraints on what kind of computing slaves they can run, right? That are registers into the underlying Mesos. So here we have, for instance, a number of tiers. We have a tier 1, tier burst, tier 0, tier Chronos, and tier GPU. Tier GPU are machines on Amazon that have GPU. Right now, there's a severe shortage of GPUs. So the last 2 days, we didn't get any spot instances on GPUs. We believe that they're releasing something new on reInvent, and right now are not following the demand. So that's actually a major problem, that our cloud provider doesn't give us the resources we want. And then tier 0 is something that we have prepaid. So this is the base system, the base, like an instance basically of anything. The website and everything runs on tier 0, so we have always a running system. Tier 1 is a spot instances tier, so anything that runs there is managed by autoscaling groups. So when these SFM things deploy, we can check this out. Like in, for instance, this is SFM. Where's this? Here, SFM atomic. So this is a scaling here. And if you look at the configuration, we have this in a cluster tier 1, right here. So this Docker container scales only on machines that are spot instances. This is stateless, so we can scale up the system for 1/10 of the price that would happen if we had prepaid instances, which is really nice. We get down the costs. So there's like two levels of scaling here. And then, of course, we can pack the containers more tightly and so on. So all the other Docker stuff you can do. Let me see, where was I? We were here. Yeah, monitoring, as I said, we are basically submitting stuff to Riemann, which is a little closure-based in-memory server, which then forwards everything to InfluxDB and Grafana on top of it, so we can do, graphing. That's what you saw, and logs are submitted to the ELK stack and so on. So how does testing work? This is like a lot, as you saw. There's a lot of like moving parts, a lot of different Docker containers, everything we need to do. So back 3 years ago, we realized that we have a major problem testing our code because it's so different things, and we cannot really demand of every developer to know everything, especially, for instance, the vision parts. They're building on OpenCV, which is really hard to install. It's like huge images that huge installs you need to do. You just taint your machine, and it's hell to get rid of that afterwards, right? When you really just want to adjust a little of Python code. So we decided to make a move, and that was right before I told you last time that we were working on something called Mapillary in a Box. That we have now taken to the next level. So basically what we're doing is that we are attaching Docker building information to every single repository. I can show you how this looks. Say we have a repository. Let me see if we have one. Here, for instance, this is not really a repository. Let me just do something. Dumper. This is a TypeScript-based Docker container, and here we have a folder called Docker. So we have a template for all our repositories where we make sure that a Docker file exists here, and we have a base image and so on, and things can be built. Like this is how you bootstrap your repository, right? And then we have a couple of scripts to make sure that they have the base stuff installed, like from Mapillary base and so on. So this is one thing. So everybody knows I can go into any repository, I can boot into that Docker image, and you see that we will here somewhere here we set up the Mapillary org source. So when you boot into this thing, you not only get the copied code into that Docker container here, right, and here, but you also get mounted when I start this with my scripts. I also mount the actual code as a source. I can go into that and then do my development locally. That is good and fine and worked for a while, but what if you actually need to test things? Especially in the Storm case, we have like Kafka delivering messages, we have concurrency going on, we have like scaling going on, which is really hard to test. So we took this to the next level and started to describe the dependencies on our repositories with a JSON file. The problem is when you just do if you take several repositories and you do, say, a Docker Compose file, right? You can craft that Docker Compose file, you boot it up, and you hopefully have a working environment. However, the boot order and the dependencies between Docker images are in Docker not defined, which makes it really hard to find the right booting order. So this is what we added, essentially describing whatever our repository is providing and consuming. If I go to my Mapillary structure, which is a file that every Mapillary repository has too, then we basically have different providers which are different code setups. You could have several, of course, providers in one repository, right? Because you want to reuse the same Docker image. But in this case, for instance, you have the, say, Mapillary dumper weekly email provider. That one is sending out emails, right? it provides a number of settings. So this is what the provider exports. So you never import config variables. We register a provider's exports into the central configuration system, which is not console or something. We could do that, but it's just a Redis database that backs, shell scripts that export these things into your shell environment, which is kind of like easy to consume for everybody. You just say like process environment, and I can expect when I have a dependency to this provider, I can expect the configuration to have a dumper email settings variable somewhere, right? So I can depend on this because of that provider. Otherwise, it will not be there, at least not in the testing environment. In the production environment, it's kind of like the sum of all settings, right? Because everything is deployed. But for testing, we can then make sure that we are not consuming variables that are not there, like stale variables and so on, which is often a problem. You don't know where things are used, right? And then we have external dependencies, which is like Google Sheets, which is another library. But this is interesting. This provider depends on other services that are, provided by other providers, which is like cluster config. We need an Elasticsearch read service, which is actually write protected. So if you try to depend on this and write, we will get a exception, which is especially important with Postgres and these things. Update table without where clause are like dangerous things. And then, we have a Postgres read, and we need some Kafka topics that we want to post to, because Gudrun is our storm cluster, because Gudrun was a big storm in Sweden, so it's our biggest storm cluster. So Storm will read this stuff and then send the actual mails, right? Then there's a command how to start like this special code thing. You see, like we have a standard boot script, but basically this is a just this start script. This is basically how the production Docker provider will be started also, right? And then you have the service that it actually provides. So this was the provider, and then there can be like different services. But this is the service that others would, it's named the same as the provider, but this is the service that other services will depend on. So this is like making a statement of all the different things this repository can do. We check this in, and from this, we create a big dependency graph. We could use kind of like Maven and everything, but it is just not working as a dependency handling system on Docker level, right? So what comes out of this is that we have a job that every 5 minutes looks at all the checked in mapillary structure files in all the different repositories, and it creates a kind of dependency graph between our services, which is actually a non-trivial thing. So if you look at this is like the dot notation graph. So these things have no dependencies, are actually faulty. That's why they are red. They have no information on them. But if you go into the main system, like this is kind of the I can see if I can get that smaller. But you see, this is, for instance, like let's see where all these things lead. You have a number of central nodes here. If we go up here, a lot of things depend on, for instance, Kafka APIs, which is kind of understandable because it's a persistent source in the system, right? But at least we know that. The interesting thing from this is a quite unwieldy version of this. What happened here? Oh, where's my, okay, whatever. But we also read this in to, of course, I come from that background, a Neo4j database. And let's see if we can maybe get that back. I hope it's online. Here we go. And I will see if I can. Oh no, they disappeared. But basically, we are reading this into graphs to be better able to query it. So I could just say, for instance, I don't know, like match n, say, developer does anything with anything, just to, oh, this should probably be something else, and then we n r e, and we might get, you know, a bit of, here's a developer called Martin Skans who's actually maintaining something here. I'm just trying, like, for instance, let's see if we have something. Mapillary Riemann server, that's our Riemann server, and there's someone else called Peter Neubauer that also maintains this thing, right? And from this, we read in more, and we can see that from this, we are deploying an application which is another file that we analyze called Mapillary Apps. So we could really do that in the same file, but basically this describes in a good way, you know, what we have on Marathon and what we have on Kronos, which is the kind of like a cron-based equivalent to running Docker images on Mesos. And here you have a, you know, we have, I don't know, like here, download stuff, and you see what tier it should be on, what constraints it has, and how many instances there should be initially before the actual auto-scaling goes in. And we connect that into this big graph, and then you can see, yeah, this is good. And then there's a number of providers. This provider, for instance, is the Riemann server provider that gets deployed as this application. So from this, we can basically analyze how are our dependencies. We are right now in the process of adding all the deployment information on that. Like every single Jenkins build that is, you know, doing something with that will add a version to all these. So we can like version all the successful builds, and then we can analyze what is actually deployed. Right now, we don't really know. There might be old stuff deployed that is like, you know, weeks old, while our code, if it is not auto-deploying, which we might not want, is not actually, you know, keeping it updated. So we might be running with old code. And the other thing is we could actually take snapshots of the whole deployment system and diff it to the whole development system. So we can see, you know, which parts of our infrastructure are outdated and who's responsible for that. Well, not to blame someone, but just to see, oh, here's old code. We might do an effort to actually get this up to date, or why is it old? There might be, you know, incompatible changes that people are not daring to deploy, and so on. So this is the beginning of actually analyzing and then enforcing rules. Also, you cannot deploy, say, if your code hasn't gone through Jenkins and so on. This is one thing. This is the kind of analytical kind of outcome of describing your dependencies. The other interesting thing is that for every single provider, we are generating then the dependency handled Docker Compose files. So we are using Docker Compose. You could use Docker Swarm or whatever, or, you know. But if you look at, say, what did we have? We had dumper, or just something that has some dependencies. Let me see if I have Gudrun, which has a number of dependencies. So the integration YML, Compose YML, is actually taking the Docker images in the latest build, like a Git version of what is checked in. So Jenkins is building every commit as it should be, publishing it to Docker Hub, and we are then putting these YMLs into like these versions into YML. So if you see our Jenkins here, you might have, you know, this master branch here, and you have a version here, right? Somewhere here in the latest build. This is our Git version of that build, and that version is then every 5 minutes built into a new Docker Compose snapshot of the whole system. So if I would go and try to, ooh, this actually went up, which is good. YML, do we have anything here? So here we have now services, and here you have, a Docker entry. We need RabbitMQ to post things to Rabbit. So there is a RabbitMQ Docker image materialized with the latest RabbitMQ version. We were thinking of actually handling branches and so on. However, the complications of this is quite enormous. It's like Maven hell. You will get basically version handled incompatible Docker image dependency trees, which is non-trivial to solve. I mean, how do you merge these actually? Like, what does it mean that you can run against the branch and not the other? And then we have, and we also decided to put Docker providers for everything that we depend on, which is, in this case, Rabbit, which we don't develop ourselves. It is actually a version of Amazon S3, which we use, but here emulate. You should be able to run your tests offline, like here, like switching off your phone, and everything should work. We're putting in, Elasticsearch in image. We're putting in this case, a Kafka provider that needs architecture is actually the configuration service that I talked about. So everything depends on the configuration service. This is the actual code, and you see here we have the image. However, this is like the binary that Jenkins built of your current code. However, if you're developing locally, you can go into cd/mapillary source, and you will mapillary dev source, and you will actually be in your own code, and you can test against a full running environment with everything set up. That's one thing, and then you have Postgres set up, you have Redis set up, and and you have Zookeeper for both Kafka and for Storm. It's needed, so we make sure we can connect these. One interesting thing is here that we have a test runner, and the test runner is another Docker container that only contains test code. It knows nothing about this like Storm repository or the code we have there, and it pulls in as a source. That's what I requested. It pulls in our testing framework, integration testing framework, as source, and it mounts the tests we have in our source, the integration tests. So it excludes all the other source, which is deployed, in another provider. It's only mounting the tests, and the tests here are this. So we have tests, integration. This is the provider we are testing, the mapillary Gudrun alt topologies, and in this, for instance, here, let's say I take this one. This is now a Python-based integration testing framework we built because we want all the integration tests to be exchangeable between code bases. So if we move code between code bases, which tends to happen, we need to move this to that, and we are retiring this repository, you basically just have to take the integration test somewhere else, execute it, and work until it works, right? So in this case, we have, let me see some interesting fixtures here. Here we go. So here we are trying to update a type of project, right? What we want is a staging system that already has something materialized so we can work with it. We only want to update things, not to insert things. And we don't want to, bootstrap the whole system. So what we do is that we have in our testing library, which we call Messy, that you saw briefly there, we have fixtures, and this fixture takes a project that is not persisted, nothing at all, And here we say, materialize this project in, right now we have no different stages, and so like just put it in the respective backend so I can work with this. So behind this, there's like drivers, and there's a Postgres driver, there's an Elasticsearch driver. We have like 2 big backends that we run to, and this one is only materialized in Elasticsearch, but we don't care. We just say, give me a project, and now I assert that when I read this from Elasticsearch, which I don't have to, we actually do the fixture transactionally, so you don't have to wait, right? But just for good measure, I'm looking and check that I can search this in Elasticsearch. It has actually come down, so I could easily just take this out. This is part of the fixture. It's there, right? Now I do changes to this project, and now I post an event with an event fixture. I don't really care where it goes. The fixture knows where this like capture project updated event. It's like these JSON things that you saw, where this needs to be posted. It needs to be posted to a special topic, blah, blah, blah. And then someone does something with these changes, right? And, you know, we have a little library that tries every second. Eventually, I want to see that change reflected in Elasticsearch, right? That's what I'm testing. So I don't really care what the system does. I'm just doing a project, it's there. I'm posting a change somewhere, and I'm just checking that magically this, you know, pops up. There's a whole bunch of stuff going on in the background, but that's all my test. So integration tests become really, really good for documentation. I can go in there and see, okay, yeah, whatever this does, I'm not a Java guy and I'm not a Clojure guy. I don't care. Like, this is the test I need to fulfill. And this is a mini staging system. So these fixtures actually remove things from the database when we do the pull down and so on. And all the keys here that get assigned to these are UIDs randomly generated and so on. So this is on a level that when this goes through, especially with the system test, this is now, the system tests look exactly the same, except we are materializing all downstream dependencies, not only, you know, potentially one step down. For instance, in this case, an integration test will only materialize, say, Kafka. And an integration test will materialize Kafka. You will post to Kafka, and, you know, that's a black hole. It will stop there. A system test will actually materialize, you know, all the other ends of whatever is talking and consuming this, and will do like a full system setup. But that is the other provider YML that we are materializing. So you just say I want a system test, and you get a few more Docker containers, right? Which is interesting if you, for instance, test the front end. You want to test if I actually upload an image into S3. You know, what does happen and how does it get processed? Can I actually see it later on the map with a blue line somewhere? You know, that's interesting. So this is roughly what it looks like to test, and it's really interesting that nowadays it's much easier to write such a test than, you know, deploy anything in the production system. We had until, you know, 2 years into the project. We didn't have staging systems either, because they get so tainted and are so heavy to maintain. So you get like relevant stuff in there that you need to test. So it doesn't make sense for a team of like 1 or 2 developers. So we were testing in production. We were doing, you know, event sourcing and idempotent events. So if something breaks, things will get runtime exception, and you fix the code until it doesn't break, which is kind of risky, but it works good if you know if you know like where you're going. But now that we are growing the team, you need this. You don't want to deploy things that are randomly doing stuff in production, right? So this is really saving our behind. And also, when this works, since the same code that is in here, like these versions are actually deployed. If I do like a deploy an app, it takes this version and pushes it into production, so we know the exact same binary code that we just tested is there, and it will probably not break. I mean, there's still stuff that can break, but that's normally production level error conditions. Things are sent in the wrong order, or someone submits, faulty data, or whatever that is. But the code level problems are basically gone. So we have a much more stable system since then, and also we can build new services. We just built a blurring service which municipalities are using to use our privacy blurring. That is basically a glorified system test. So we took a system test setup, put there another repository which is just keeping track of accounting and basically submitting to billing, deployed it on Amazon, and off you go. So it's just an entrance to, blur these images, right? So this is how we basically test. Any questions on this? Okay, I can show you briefly also the other part of the equation, which is messy. So let me open that. Messy is the testing kind of Python framework we do, and here you have like the interesting things here are that we have that it's really small, right? It's kind of hard to see, but basically we have the normal stuff. But interestingly, we have fixtures, which you just saw. For instance, if you say Elasticsearch fixtures, say we have a mapillary user fixture. See that? This is a Elasticsearch user fixture. It takes an Elasticsearch user driver and it puts stuff into Elasticsearch. And the drivers here, we have a driver for basically anything. Takes a while to do it, but since it is so reusable, say the user driver here, it then just puts stuff down into Elasticsearch. It fills like a JSON structure and puts it in there. Same thing for the Postgres version of it. We kind of build a shadow system that knows how to persist things, right? But it's really just for making fixtures and checking stuff. It knows how to post things to Rabbit. It knows how to, but it's more or less just to take away the tedious things of the tester. Also, it knows how to remove things, which is non-trivial. For instance, in the Kafka case, it needs to keep track of, because this is append only, and we don't want previous tests to taint the next tests. It actually needs to back out that message that is just posted in case of failure and cleanup. It needs to like pull it out there so the next test can continue. So this is where we put the effort here, and then you have the domain model, and you do things. Also, interesting fact, in event-based system, we have had problems with the type safetiness of JSON. We are now using Avro. I don't know how many of you know that. It's like an XML schema for JSON, and Kafka supports it. There's JSON schema too. There's other techniques, but basically we're not production testing this, because that would mean that every message needs to be checked against a schema, which if you have a couple of thousand messages per second per topic, is a considerable overhead, and the code doesn't change really. So what we build is to build it into the Kafka drivers. So we have data here, and we have Avro, and we have all the schema for all the messages that are sent, which says, oh, there has to be like a record with a name, with so when these are in tests submitted to Kafka, they're also checked. So your test code will make sure your events and so are in order, and it also, we're thinking of generating code from that, and so you can do all sorts of interesting things then. But this makes reasonably sure that even your runtime system, which potentially accept anything, is in order. So there's different aspects to this. This is basically what I had. I hope I haven't gone over my time. 4 minutes left, or no? I'm over. Okay, any questions? Yes?
Can you explain why you use Python for testing, and you say you use Closure for coding?
No, like every repo is basically using their own language. We have tried to standardize anything kind of scripty into TypeScript, because our developers are coming around from JavaScript and Ruby and Python to have more type safetiness. And anything other, like Vision Code, is much Python because of the domain, and Storm and so is much Java. Elasticsearch, you know, it's a mix. That's why we have all these different code bases, and we don't really want to constrain ourselves to rewriting everything in the language that we like. And then the other question was Python. Yes. So we just realized that Python is probably the most easy language to read, and our tests are much for the documentation, and they need to be easy to move. So the threshold of writing a Python test is probably the lowest you can have. If you have something like what I just showed you, we have developers and you know, other members of the team who get productive with integration testing. Within like 2 hours, they start the company. They write their own integration test, which is actually executing, and they have never entered the VPN because we do everything, you know, locally, so they don't need any production grade, you know, restrictions removed. So that's very positive, and they still can see the full system. They can learn, they can examine all the code, but they cannot go into production. It took us like 3 weeks to remove all the variables that were hard-coded from all the Docker containers, like pulling out the plug, executing. Oh, this is not there. Oh, this has been hard-coded. Oh, let's remove it. So it's interesting. Okay, I won't keep you longer. Thanks.